calculating KSP problems, the best thing to do is to write a reaction showing the dissociation of the ionic solid. And so our solid is zinc hydroxide. And when it dissolves, we're going to see its KSP is pretty small, so we know that it's in equilibrium. So it's going to have a zinc ion, zinc plus 2 hydroxide ions. So if we wrote an equilibrium expression for this, we would get zinc plus 2 times the concentration of OH minus raised to the second power. And there's nothing on the bottom because my reactants are solids. We only include AQ and gases in equilibrium expressions. So those are the only two that go on KSPs. And so we know that's equal to KSP. Well, we can see what they're looking for is solubility. And what solubility is basically X. It's the concentration of the ion at its lowest level. So it's X. So when we work this out, I know I get X amount of this if this breaks up, but then this is always going to be 2 times more than that. So this will be 2X, or 2 times the solubility. So then if I plug those in, I get X times, well, this is 2X, and then raised to its coefficient squared. And then I look up there and I see that the KSP is 7.7 times 10 to the negative 17. So then my goal is to solve for X. And so if I multiply, or I go ahead and expand this, I get 2 times 2 squared is 4, X squared times X. And so if I combine terms, that's 4X cubed. And that equals to 7.7 times 10 to the negative 17. So the way I solve for this is I'm going to take my KSP, I'm going to divide by 4, and then I'm going to cube root it or raise it to the 1/3 power, and that's going to give me the value for X. So if you do all the math on that, you find out that the solubility is 2.68 times 10 to the minus 6. Make sure you practice that to make sure you can get that value in your calculator. So that's the first question. Now, the second question from this problem is now it wants you to start with a reaction, and you're going to form a precipitate in the problem, but you need to know how much. Like this is really a great problem because it starts off as a limiting reactant problem. So what I'm going to do is I'm going to write the reaction. So I'm going to have zinc nitrate plus some sodium hydroxide. And if I double replace this, I end up with some zinc hydroxide and some sodium nitrate. Now, if you're in my AP class, then you're going to see that I always say that group 1s and nitrates are figments of your imagination. You see, these are all AQs, except that we know that this guy is going to form a solid. Most of the time, you can see that it has such a small KSP that majority of it is not going to dissolve. So what I do is I get rid of, let's just get rid of those things that are a figment of your imagination. The nitrates are gone, so this becomes ionic zinc plus 2. The sodium's gone, and this becomes OH minus 1. Notice I haven't balanced yet, and so the sodium and the nitrate are gone. So what am I left over with? Well, let's write that out. I got some zinc plus 2 plus some OH negative 1, and I make my zinc hydroxide solid, and that is my net ionic equation. Both of these are AQs, but I need to balance, so I need 2 hydroxides to take care of that guy right there. So this is my reaction. Now we're going to do a BCA table. So before I start, how many moles do I have? Well, it shows me that I have 50 milliliters of 0.1 molar and a zinc nitrate, or that's going to be my zincs. And so if I multiply my 50 milliliters times my 0.1, I'm going to find that before I start, I have 5 millimoles of zinc. So I'm going to do the same thing for my NaOH. I have 50 milliliters, and I have 0.3, so 50 times 0.3, I have 15 millimoles of OH. And to start with, I don't have any of that, and honestly, I don't really care about the solid because it's not going to be part of the equilibrium. So then what is my change? I need to decide which one of these is my loser. And so who is going to limit my reaction? So I know I need twice as much OH than I do zinc. And so I go over here and go 5 times 2, that's 10. I need 10 OHs to make this work. Oh, I have more than enough. I have 15. So I know that this guy is going to be my limiter. So whenever it's your limiter, if you remember way back from limiting reactants, that you write that guy down. And I'm just going to go ahead and write it down over here, and we're going to go ahead and work out our solid, even though I really don't need it. So I have 5 millimoles under everybody. And then, what are the ratios? Well, I know zinc has a 1 in front. And so I'm going to take his 1 and put it on the bottom. And then I'm going to take their own numbers and put it on top, which is going to give me those ratios, which we already saw. That for 5 moles of these, and I'm going to have to react 10 moles of those, and I'm going to get 1 mole of zinc hydroxide. It's a 1-to-1, so 5 moles. And so to work out the after line, remember that the after line is when we work this out, so I know that this comes out to be 5 millimoles. 2 times 1, this is 10 millimoles, and this will be 5 millimoles. Let me go ahead and separate those. And so what I'm saying is that I start with 5, I use 5, so how much do I have left over? None. I start with 15, I use 10, so how many do I have left over? I have 5. I start with none, I gain 5, so I get 5 millimoles of my solid over here. So now, the question is what is the concentration of the zinc? Well, don't think there's none, because there is a KSP. Some of this zinc will dissolve. And so what I need to know here is I need to know the concentration of my OH, because now it's going to become a KSP common ion problem. So if I know I have 5 millimoles, what is this all floating in? Well, there's 50 milliliters, if we remember, of the zinc nitrate, and there's 50 milliliters of the NaOH, so this is all floating in 100 milliliters. So what is my molarity? So 5 divided by 100, very simple math here, move the decimal over 2, I have 5 molarity, 0.05 molarity. So what now? Well, now we're ready to do a KSP problem. So we just did a limiting reactant. Those tricky people making us do a limiting reactant inside a KSP problem. So I have my zinc hydroxide, and we know that at equilibrium, I'm going to get zinc and 2 hydroxides. And I don't care what the concentration is, because this is a solid, so I don't really care about that. It's not dissolving, so I have 5 millimoles of it, but it doesn't make any difference. I need to know my zinc. Well, to start with, I'm going to say I have 0, but I have some of this floating around. So if we do our RICE, so this is our initials, and then what's our change? Well, our change in this case is going to be plus x and plus 2x. So at equilibrium, I'm going to get x amount of this and 0.05 plus 2x the amount of that, but look how small our KSP is. 7.7 times 10 to the negative 17. That x is going to be so small that it won't matter, so we can omit it. So now we're ready to plug back into our equilibrium expression. Well, let's write that again, since I don't have it sitting right here. So let's write our equilibrium expression. So it's just going to be that our KSP is equal to our zinc times our hydroxide squared, because of that 2 in front. So now I'm going to plug in, well, zinc is x, OH is this 0.05, but we are omitting this plus 2x, so it's just 0.05 squared, and our KSP, 7.7 times 10 to the minus 17. So very simply, if I take 7.7 times 10 to the minus 17 divided by 0.05 squared, I get x. So if you work all that out, pretty small number, when you work that out, and you get 3.08 times 10 to the minus 14. So I get that x over here, 3.08 times 10 to the minus 14. So what is x? Well, x is our concentration of zinc. And so if we look then, we know that our answer, our zinc plus 2, is equal to 3.08 times 10 to the minus 14 molarity. Well, what is my OH minus? Even though it didn't ask us that, it's kind of nice to always write things down. So our OH minus, remember, is going to be 0.05 plus 2 times that number. It's not going to make any difference because it's not enough to make any difference on significant digits, and so it's just 0.05 molar. So that's how we do a KSP problem when it's asking for a concentration with a common ion.